In this part, we will continue our discussion on implementing a queue in CPN tools. So far, we have seen different ways of implementing timing behaviors in CPN tools. If you are watching this part without first watching the previous one, we strongly recommend that you watch at least the first half of the part 1 video, where I have given a brief introduction to list color sets. Coming back to our discussion on the timing behavior as it is implemented in CPN tools, this was the example in front of you we were discussing in part 1, where we added this Selfloop place to this transition called server in order to behave in a certain way. So if we have incoming jobs, and this server can take one job at a time, and it can only take the next one after it is done processing the first one, that behavior can be implemented using this Selfloop place. So just to give you a quick refresher on how it works, we have 3 incoming jobs. The first one is available at time 1, the second one is available at time 5, and the third one is available at time 7. The Selfloop place has a token with a timestamp of 0 on it. So when we fire this transition at time 1, because the job 1 is available at time 1, this is the earliest time when this transition can fire with tokens in its input places. So when we fire that transition, we see that job 1 appears at the output place with a timestamp of 11. So this is the time when this will be processed, this job will be processed. The Selfloop place also has a token that says 11, because this token also gets its timestamp updated the way we described in the previous video. If we go to the event clock, at this time it says that the current time is 11, and the current time 11 is the time when this transition can fire the second times, and it is because of this Selfloop place and the token in it, because this token will not be available at time 11, so this transition cannot fire any time earlier than that. Now, with this present time being equal to 11, the input place, incoming jobs, has 2 tokens, and now these 2 tokens both are available at time 11 because both of them have stamps smaller than this 11. So when we try to fire this transition server, it asks as to which of the 2 tokens would you like this transition to fire. So you can fire it with job 2 or you can fire it with job 3. If you are running CPN tools in the automated simulation mode, the simulator will randomly select one of these 2 available tokens. So in the previous example, we selected job 3, but we can as well select job 2 and run this transition with that and fire it. And you see that job 2 gets a stamp of 21. The third time it fires, the time on the clock is 21. Because of this Selfloop token, it will not be available until time 21. So the third time this transition fires, the time must be at least 21. And when it fires with job 3, the job 3 gets processed at time 31. And we discussed that the way this timing behavior works in this example, the incoming tokens are not queued. They don't. The input place does not have a first in, first out. We saw that job 2 and job 3, although job 2 arrived at time 5 earlier than job 3, but since the next time this server became enabled at time 11, both of them were available in the input tokens. There was no queue, implicit queue in that place. Therefore, any of those 2 jobs could be picked up by this transition. Now, what about if we wanted to have a queue in this input place? So the question is, how do we implement a queue? How do we enforce this first in, first out strategy on the incoming tokens which are inputs to the server? In order to do that, we'll have to use the list color set. That's the only way we can implement a queue in CPN tools. So let's do that. Before we do anything else, I'll show you the new list color set that I've declared to implement this queue. Remember that we have this color set job. Let me go and show you the definition of job. The color set job has 3 elements: job 1, job 2, job 3. I have also declared this time this color set job list. It's a list of job. This is the definition over here, and I have a variable also declared JS, which is of type job list. This is the only thing I have done. All the other color sets we have discussed before. So the new color set I've added is this job list job. It is untimed. I have added the timed keyword at the end of it. And with this definition, and let me close these things and come back to our Patrinet structure over here and show you how we can add a queue to it. In order to do that, I'll first delete this link between this input place and the transition that says server, and insert a queue, a place that will model the queue in this new Patrinet model. We'll call it queue, QUE, and I will also add a transition. Let me place them. This transition will put things in the queue, so I'll say form queue. And now I will have my incoming jobs coming to this transition which says form queue with the same old expression J. So now things will be coming in to this transition, and this transition will form the queue in this place, which will have a queue in it, and this place queue is assigned this new color set job list. Okay, so now what I have done is I have created this transition and place pair to implement the queue between our incoming jobs and the server. The next thing we do is we create input and output arcs from this queue. So this queue has both input and outputs to this form queue. What comes into this form queue from this queue will be we'll write an expression, but before we do that, let's put a token in this queue. Initially a queue is empty, so we'll just put a null list in it. Okay, so what we are doing is we have created a queue. Initially it has nothing in it, so we have put this null token in it, and now we can look at the expressions. So what happens is when an incoming job comes to this form queue, this queue is presented to this incoming job, and the incoming job is added to this queue. So how do we do it? We supply this queue to this form queue, so that it's like presenting this queue to this form queue transition. So JS is a variable of type job list, therefore we use it over here. The next thing we do is, let me bring this expression over here, and I'll first write an expression and then I'll explain it to you. Why am I using this expression over here? Okay, what I have done over here is I have used this JS. So JS goes as an input to form queue, but when it comes back to this place, the expression says JS concatenation operator double hats and then J inside a list. So what I'm doing is I'm using this list JS, which is initially is null, and then adding the incoming element J, which is coming from the left hand side, in that list at the tail end of this list. So JS is the queue, existing queue. Initially it is empty, but when we'll run it, it may not be empty when there are jobs in it. And then any incoming job J should be added at the tail end of this queue. Therefore, this expression, which uses the concatenation operator, it uses this J inside this list, because concatenation is an operator which requires both its arguments to be lists. Therefore, I'm explicitly adding this J as an element of a list. Okay, so I'm adding this list which has just element J in it as list added to the existing queue. In other words, I'm only adding a single element at the tail end of the existing queue that I have. So that's how the queue is formed. Okay, what happens at the server end? Again, we'll have inputs and outputs, both to this place from server. When this queue place, let me create some space here. Okay, when this server gets an input, it gets it as this expression, and I'll explain as to why am I using this constructor, 2: construction, double colon construction, j2:js, because at this server I would like to remove the first element from this queue. So if I present this queue as j::js, what I'm doing is I'm presenting this queue as the first element, double colon the rest of the list or the rest of the queue. When I do this, I can very easily return the JS back, which is the rest of the queue after the first element has been removed from it, and put it back into the queue. And I can take this J and use it with this transition, and then put the same token at the output place, which says process jobs. So this structure that I've added in the middle is what implements the queue. So what happens is the jobs are coming in from the left hand side. This form queue transition puts those jobs in the queue, and if there are multiple jobs that cannot be processed at the same time, they are put in the queue, and then server takes the first in first out job. That's how this is the scheme that is implemented with these expressions over here. So it takes out the first job in the queue, processes it, and then goes for the next job in the queue. Let's run it and see if it actually does it. So when we fire it the first time, we'll also look at the time. The time is 1. Job 1 is available at time 1. Form queue is enabled. It fires. The job 1 goes into the queue. It enables the server. The time still is 1. Server can take it. Server takes the job, runs it, and the job is processed and gets a timestamp of 11. The self loop timer also get a token with a timestamp of 11. Now, if you look at the structure, form queue is again enabled. We go to the event clock or simulation clock. The simulation clock now says 5. This is the next time something is available. The form queue is enabled, not the server. So form queue is fired, and we see that job 2 is added to the queue. We see a different behavior this time. The server is not enabled. Instead, form queue is still enabled. Why do we have form queue enabled? Because the clock time says 7. This is the next time something is available. Server is not enabled at this time. It will be enabled at time 11, which is determined by the self loop token stamp that it has as one of the input places. So we fire form queue again with job 3, and you see that this job 3 is also added to the queue, but it is added at the tail end of this queue. So in the list, if you look at this list, job 2 is the first element in that list, job 3 is the second element, and now we see server to be enabled. We go and look at the time, the current time. It says time 11. The server is enabled at time 11 because it is done processing job 1. When it is fired at time 11, it takes the first element from this queue, and this time it is job 2. So we have the first in first out policy implemented. It takes job 2, works on it, puts a timestamp of 21. It is enabled again. We go to the event clock. The current time now becomes 21. This is the next time the server will be able to take something from the queue. Since we have a job 3 in that queue, it takes that job and processes it and returns an empty queue back to this place which says queue on it. So that's how we have implemented a queue using CPN tools. If you have understood it, very good. If not, just remember that this structure in the middle is what implements a queue in CPN tools. So if you have a need for a queue in your model, just use this structure to have that queue in that Petrinet model. Hope you enjoyed it. See you next time. Here are some links that you may find of some use to you while implementing queues. The second bullet over here has some material on implementing stacks and priority queues. Interestingly, the same structure that we have used for queues can be modified slightly to implement stacks and priority queues. Hope you look at that material. See you in the next video.